Hi, welcome to part 2 of the King's College doubleheader. Talk 2 is Alexandre Stauffer, who will tell us about mixing time of random walk on dynamical random walk.
Thank you, Tyler. Thank you, the other organizers, for the invitation to speak here. So I'm going to talk about a random walk that moves in a dynamic environment, so a graph that changes over time as the walker walks. I'm going to talk about two very specific concrete models, but before, let me tell you a little bit of a more general model of what I'm looking at. So I'm going to look at a finite graph. In particular, I'm going to look at the torus of side length n, but you could think about any finite graph you like. And the edges of our graph will be in either of two states, either open or closed, and the state of each edge will change over time according to some dynamics. And the models will get specific by choosing the dynamics on which the edges evolve. And I'm always going to call eta t of an edge E, which is going to be 0 or 1, meaning that if it's 0, that the edge is closed at time t, and if it's 1, that the edge E is open at time t. Okay, so that's the general dynamics of the environment. And on top of this, I'm going to put a walker that starts at the origin of the torus, or if you have another graph, you just put a distinguished vertex and start the walker there. And the walker jumps at rate 1. So it jumps in continuous time, and you can also think that the graph here, the environment, also evolves in continuous time. The walker jumps at rate 1, and whenever the walker decides to jump, what it does is it chooses a neighbor on the graph. It doesn't look at the state of the edge. It chooses a neighbor on the graph, and then jump over that edge of the chosen edge if the edge connecting it with its neighbor is open at that time. Okay? Or another way to put this, say that the random walk is just doing a continuous time, simple random walk on the environment, but suppressing any jump over closed edges. Okay? And then we're going to denote by xt the position of the walker at time t. Okay? So that's the model. So just a few remarks. If eta t is a Markov chain, and in this talk we're always going to look at Markov chain and also irreducible and periodic. So the full system composed of the walker and the environment is also going to be a Markov chain. And in the case of the torus, the stationary distribution of the walker is just the uniform distribution. For a general finite graph, it's just the stationary distribution of simple random walk on that graph. Okay, that's what we're going to look at. And the question I'm going to be interested in looking at is the mixing time of the walker, or if you prefer, of the full system, walker and the environment, since this is a Markov chain. So just a remark here, if I look at only at the walker component, of course, this is not necessarily Markov. So if you are feel more familiar with the mixing time of Markov chain, then you can look at the mixing time of the full system. In the case we're going to look at, they are not going to be different. If you don't write mixing time at all, you can just think about having two copies of the full system, two copies of environment plus walker evolving, and you want to find a time for which if you couple the evolution up to that time t with at least probability half, you can couple them precisely so that the two environments are the same and the position of the two walkers are the same. That's what we're going to do at the end of the day.
You mean that you try to find a good coupling?
You try to find a good coupling, yes. Okay, so let me talk about the more concrete models, and the models will just be determining the dynamics on the evolution of the environments. And the first one is the simplest, I think, that is non-trivial. It's dynamical percolation. So what means I start with IID bound percolation, so each edge is open independent of each other with probability p at time 0, and then they evolve according to dynamical percolation. It means there is a parameter mu, which is the refresh rate of the edge, so each edge refreshes at the rate mu, and when an edge chooses to refresh, then it just flips a coin and becomes open with probability p, closed with probability 1 minus p, independently of its current state, independently of all the other edges. You just do this independently. That's very simple dynamics. One thing that I want to be clear here is Of course, I'm going to look at the mixing time of the walker as n goes to infinity, as the size of the graph goes to infinity. And mu here should be seen as a function of n, and I'm going to be mostly interested in the case where mu is going to 0 as n goes to infinity. So the environment is changing slowly, because the walker is jumping at rate 1, but the environment, the edge refresh at a rate that's going to 0. Okay, that's actually the most interesting case. On the other hand, p for me is just a constant. I don't care for p, and I will hide p, any dependence on p in constants. But for me, mu, I want to make the dependence on mu explicit. Okay, and one feature that I also want is that the processing is, the environment is in stationarity. Okay, so that's why I start with bound percolation, so that at any given time t, if I look at the probability that an edge is open, this is just p. Right? It's in stationarity.
So I didn't get it. Is that periodic boundaries?
There are periodic boundaries, yes. Just the torus. Yeah. Okay, so what should we expect about this? So look at the walker evolve in this dynamic percolation environment. So what to expect, the conjecture is the following, that for any dimension, we have I would distinguish two cases. One is if p is smaller than pc, pc being the critical probability for bond percolation on ZD. So if you are in the subcritical case, then the mixing time should be n squared over mu. And this just means up to constants that do not depend on n or mu. So why this is the case? Well, it's subcritical. So the clusters are of open edge of order 1. The walker is typically in one such cluster. It moves at rate 1, so it's moving a lot. Yeah? And the cluster takes time 1 over mu to actually change, because it has order 1. So so the walker has to wait times of order 1 over mu for something different to happen to the walker. Right? And when this happens, you could expect that what the walker is doing is some kind of random walk. Each time its cluster changes. So if you believe on this kind of very vaguely and heuristic kind of reasoning, you can expect that the walker will take n squared such times to mix, just like in the torus, but each step takes times 1 over mu. So that gives you n squared over mu. So that's a very basic heuristic, but actually I'm going to give you a less basic heuristic later on about this n squared over mu. If instead we're in the supercritical case, p bigger than pc, then we expect the mixing time to be different, to be of order n squared plus 1 over mu. Okay. It's easy to see why the 1 over mu is here, because, well, we start at stationarity, so with positive probability, the walker is in a small cluster to start with. Actually, with positive probability, all edges adjacent to the walker at time 0 are closed. So the walker is stuck. And it has to wait a time 1 over mu for even getting out of its initial position. So it needs to pay the price of 1 over mu. But then after 1 over mu, you can actually see that the walker has a very good positive probability of chance of being connected to the giant cluster of the torus of open edges. And when it gets to the giant cluster, then it walks a lot. And actually, you can show that after it first gets to the giant cluster, it spends a constant fraction of its time in the giant cluster, and n squared steps in the giant cluster should be enough to mix. So you pay 1 over mu to enter the giant cluster, but then after n squared steps, you mix. Okay? So that's essentially.
But occasionally it can be isolated on small islands.
It does. It does.
It adds up to the 1 over mu.
But the thing is, after it enters the giant cluster, it spends a fraction of its time. A positive fraction of its time in the giant cluster.
You have that little means you have a big constant.
I have a big constant, yes. Okay. Any more questions? Yeah?
So at PC?
Very good question, and I have no conjecture for that. Should be somewhere in between, but I won't commit to an answer to that. Okay, so, and what do we know? So those are the conjectures. The first is actually a theorem. It's a joint work with Yuval Perez and Jeff Stife in the old days. We proved that the mixed time is actually n squared over mu. We prove upper and lower bounds that differ just by a constant that depends only on the dimension and p. The second regime, it's almost a theorem. It's a joint work of Yuval, Perla, Susi, and Jeff Stife. They show almost this result, but they show this for p large enough. They don't get this for all p bigger than pc. So for p large enough, and they lose a polylog factor in the mix. Okay. And for the critical value, that is nothing essentially known. The only thing that's known is that the mixing time is at most n squared over mu. But there is no lower bound that's close to that. Okay, there are other results on this. There are results on the complete graph. There are results. There are some bounds, general upper bounds that hold for more graphs. There are recent studies on biased walks. Many open problems like the critical case, and even to close the gap in the supercritical. But what I'm going to do today is something different. So what we want with this work, the work I'm presenting here, is to start looking at the case where edges do not update independently of one another. So we're going to shift a little bit direction here, and we get to our second concrete model, which are going to look at the random walker evolving in another kind of dynamic environment, which is given by the random cluster model. Okay, so the initial configuration is just the random cluster measure on open and closed edges. Again, edges are either open or closed. And the probability of a configuration is just given by p to the power of the number of open edges, 1 minus p to the number of closed edges, just like in Bernoulli percolation, but adding a term q, an extra parameter, to the number of connected open components, open clusters in your configuration. So don't worry if you're not familiar with the random cluster. I'm going to actually tell you all the properties we need from the random cluster in this talk. And then after we start with the random cluster measure, the dynamics is just going to be Glauber dynamics of the random cluster measure at rate mu. So again, we have a rate mu for edge to update, and then they update according to Glauber dynamics. But for the random cluster, we can precisely describe what the rules are for each update. And that's what I'm going to do now. So whenever an edge chooses to update, this happens at the rate mu, then either of two things happen. So the edge has to check whether it's currently what I call a cut edge in the current configuration, or whether it's not a cut edge. And what does it mean? So an edge is a cut edge. So I have an example here to illustrate this. So the edges I'm drawing here are the open edges, and the edges that I'm not drawing like this one are the closed edges. And an edge, which can be either open or closed like this one, is a cut edge if there is no path between the endpoints that do not use the edge. There are no open paths between the endpoints that do not use this edge. For example, here there are no open paths at all that connect these two endpoints. This is another cut edge. There is an open path between these two, but all of them use this edge. So there's no open path that goes from one point to the other that does not use this edge. Okay? Otherwise, an edge is not a cut edge when this does not happen. For example, this edge here is not a cut edge because there is this path here that connects the two endpoints and they're open. Okay? So whenever an edge decides to update, it looks at the current configuration, see whether it's a cut edge or not. And if it is a cut edge, then it becomes open with probability p divided by p plus 1 minus pq. Otherwise, it's closed. And if it's not a cut edge, then it becomes open with probability p, otherwise it's closed. Okay? So that's the main difference, that the updates now depend on the current configuration of the graph. And again, we chose to start with the random cluster measure and do Glauber dynamics. We're still in stationarity in our case. Right? At any time t, the probability of a given configuration at time t is just the random cluster measure of that configuration.
So to check this, I mean, is it like order complexity n squared or n log n? To check if it's a cut edge, like a true cut edge.
Yeah,
It's quite expensive.
It depends. I'm not going to stick to an answer. In some cases, we know how long it takes, but not in all cases. It also changes depending on the values of the parameters. Okay. And now there is an extra parameter q here, which for me is, again, is just a constant. Right? Q and P are constants. Mu is the parameter for which I want to get explicit dependence.
Q is larger than
Not necessarily. And of course, Q equals 1, you get back to the dynamical percolation. So the term here in the measure Q disappears, and you get exactly the independent percolation measure. Okay, so what are the results we have? We have the following. So for any Q, any dimension, if P is small enough, then we recover that the mixing time is at most a constant n squared over mu, like in an independent percolation. So it's an upper bound like in the independent percolation, but we don't get this all the way to the critical value. We need P to be small enough.
And you don't use any. Okay, I know why I asked you.
No
So
FKG.
you don't have FKG. Then.
We don't have FKG, but we don't use it. But of course, if P is small enough, then you are bounded by a percolation process. Right? Yeah.
But if I remember correctly, you said that in the percolation case you have this upper bound for every P, no?
You have the upper bound for every P, yes. Not here. Okay, and we also have lower bounds on the mixing time, which match the n squared over mu. And this is a little bit more precise. So if Q is bigger than 1, then we can get a lower bound that matches the one above for all P bigger than, smaller than PC. Right? So you get the mixing times at the least constant n squared over mu for all subcritical Ks. But if Q is smaller than 1, then our lower bound of Cn squared over mu is only for P small enough. Okay. Okay. So now my goal for the rest of the talk is to give you the ideas on the proof of the upper bound, which is the hardest one, this one here. So the lower bound is easier. So essentially the lower bound, the strategy for getting a lower bound is to say that if I have a very small constant, if I take a time that's a small constant and it's square over mu, then I want to say that the walker cannot reach even half of the torus. So the maximum displacement of the walker from its original position is at the most n over 3. So that's the strategy. This already implies that the mixing time has to be bigger than that. For the upper bound, we have to do more. And before I enter into the proof of this result, I want to tell you an ingredient that we already use for dynamical percolation, which is going to be useful here for the random cluster. So the next 2 slides, it will be about the dynamical percolation environment. So you can imagine from now on, for the next 2 slides, that the edges are just flipping their states independently of one another. And the idea to get an upper bound on for mixing time of the walker on the dynamical percolation for the subcritical, and for now on until the end of the talk, I'll just talk about the subcritical case, is to enlarge the state space of the environment. So now we're going to enlarge the state space of the environment. We're going to say that each edge of our environment is going to be in either of 3 states, 0 meaning closed, 1 meaning open, and a state called star. And I'm going to say that an edge is at state star if it has been refreshed since the last time the walker visits that edge. Okay? So just to illustrate this, in other words, if you look at a piece of the torus here and draw in black the open edge, say in dashed red, the closed edge, and I don't draw the star edge, so now the not drawn edges are star. What happens here is that all edges adjacent to the walker are either open or closed, always. And if an edge that's not adjacent to the walker, like this one, refreshes now, then it becomes a star. I don't observe whether that edge becomes open or closed. I just defer this observation for when the walker gets there. Okay? If an edge that's adjacent to the walker refreshes, then I do flip a coin, and with probability P makes it open, probability 1 minus P makes it closed. I just observe it immediately. Okay? So that's the process. And the nice thing about this these enlarged environments, that if we get a configuration where all edges adjacent to the walker are closed and all the other edges are star, not only I get the walker stuck in a position, but I actually get a very nice and clean regeneration time. So I just need to observe my process between such times, right? What's going on at each regeneration time. You can imagine that in this business, having a regeneration time gives you everything, right? But for the mixing time is a little bit more subtle. And how do we use the regeneration time to get an upper bound of the mixing time? It's a very simple idea. Is the following, that once we are in a regeneration time, and I'm drawing here a picture that has a small portion of the torus, so all edges close around the walker and all the other edges start, so we are in a regeneration time. There is a sequence of events that happen with positive probability, which are the following. So first, nothing happens. We have to wait one of these 4 edges to open for something to happen. And suppose it's the one to the right that opens. And once this edge opens here, when the walker traverses it, we have to sample and observe what the state of these 3 edges, whether they are open or closed. And with positive probability, they will be all closed. Just 1 minus p to the third. They will be all closed. And if this happens, the only thing that will occur is that the walker will just, banging his head back and forth over this edge, waiting for something to happen. And the next event I ask is that this next thing to happen is that the middle edge here closes. When this middle edge closes, then the walker will be in either of the 2 sides, and actually with probability roughly a half. So I can actually say that with positive probability, I can really couple the walker being probability half of being there and probability half of being here. And then the final thing I'm requesting here is that when this happens, and let's suppose the walker is here, I ask that all the edges that are not adjacent to the walker refresh before the edges that are adjacent to the walker. And if this sequence of events happen, I'm back to regeneration time. And the only thing that happens is that the walker did 1 step to the right or stayed put with probability half. And the reason why it chose to the right is just because the first edge that opened here was the one to the right. If it was the one above, it would have done a step above with probability half or stayed put with probability half. In other words, after all the sequence of events happen, what the walker did is just 1 step of simple random walk. Okay? This happened with probability, positive probability. So whenever we are in a regeneration time, there is a positive probability event that says that the walker just does a simple random walk steps. We call this a simple random walk moment. And that between 2 regeneration times, there's a positive probability of having a simple random walk moment. So then that's essentially all you need for the proof of the mixing time, because n squared steps of simple random walk is enough to mix on the torus. The time it takes between steps is of order 1 over mu, and then it gives you n squared over mu as an upper bound. The fact that the time between regeneration times is of order 1 over mu, that's the hardest part of the proof. Okay? It's the part that really uses subcriticality, and it's the part that I'm not going to tell you, because it's going to be useless for the random cluster. But that's the proof. The main idea that we're going to use for the random cluster is the idea about the regeneration time, the star edges. So now I'm ready to go back to the random cluster. Is there any question about this part? Okay. So let's go back to the random cluster. So now edges do not update independently of one another. So I want to adapt the definition of the star edge so that we get, again, this nice independent from the past. So what we do is the following. We know that in the random cluster, when an edge updates, let me move here, what I'm going to do is I'm going to first sample a uniform 0-1 random variable. Okay? And then I know that if an edge is not a cut edge, and I write here the interval 0-1, if an edge is not a cut edge, then if my random variable u is before p, so between 0 and p, I know that the edge is open, otherwise it's closed. And if it is a cut edge, if it's before P over P plus 1 minus PQ in this interval, then I know it's open, otherwise it's closed. So if by any chance U falls to the left of the minimum between these two P values, or to the right of the maximum, then I know for sure that I do not need to look at the configuration to know whether the edge is open or closed. Right? So if it falls in the left side here, I know it's open. If it falls here, I know it's closed. But I don't observe it to which side it falls. I just call it star. So those are my star edges, and I call such an update oblivious. So whenever the U value of that update falls into one of these two intervals, I just call the edge star. I call it an oblivious update, and that's it. I keep it star. If the U value falls in between the two P's, then I need to observe whether the edge is open or closed, which means I need to observe whether the edge is a cut edge or not, which means I go to the endpoints of the edge and I explore the two open components until I can decide whether an edge is open or closed, or is a cut edge or not. So in this procedure, I may run into a star edge that I need to resample to observe whether they are open or closed. I just do it, right? Until I can decide whether the edge I'm updating is a cut edge or not, and then I can decide whether it's open or closed. Okay? So that's the procedure with the enlarged space for the random cluster. Is that clear? Okay, so just some remarks. Again, as before, the edges that are adjacent to the walkers are never set to star. I always observe whether they are open or closed. This implies exploring the graph around the walker. Yeah, I don't need that. But the main thing that I need is that the probability that an edge is oblivious is just the length of the union of these two intervals. So it's just it's something that goes to 1 as P goes to 0. So essentially, most updates are oblivious. And that's one place where I need P to go to 0. Right? I need P small enough so that I have most edges updating to a star, doing oblivious update. Okay? There are many other places I need P going to 0. So that's not the only one. Okay, so now let's see how we're going to use these star updates to actually bounce the mixing time. And the idea here is to do a coupling strategy. I have 2 copies of the full system, 2 copies of environment and walker, and I want to find a time and a good coupling such that at that time the 2 environments are identical and the 2 walkers are at the same position. So there are 2 components to this coupling. Right? I have to couple the environments and the walker. Let me start with the environment, which is the easiest one to describe, and it's just these 3 lines. What I do is I observe 1 copy, and whenever an edge in that copy does an oblivious update at time t, then I'm going to do an oblivious update at time t in the second copy in the same edge, but from the point of view of the walker. So if edge E update does an oblivious update in copy 1, then the edge phi, I should be a t here, okay, in subscript. Phi t of E is updated at a second copy, whether phi t is a translation map that sends the walker from the first copy to the second one. It's just a translation map on the torus. Okay? So if the edge to the right of the walker does an oblivious update, then so does the edge to the right of the walker in the second copy. So that's all we do when we couple the environments. If an edge does not do an oblivious update, then you can try the best thing you can do to keep coupling things. But it will be enough to do to couple the oblivious updates. So some remark here. First, anytime I do an oblivious update, then I couple the edge. Right? I'm coupling the environment. The oblivious update help coupling the environment. When I do a non-oblivious update, then I may uncouple that edge that I'm updating, but more than this, I may review star edges on the way. I may review several of them. And then one thing here, there is the strategy that we're doing for the dynamical percolation of getting to origination time where all edges, but the ones adjacent to the walkers, were star, are not going to work here because I'm always going to have a density of non-star edges. There is a positive probability of doing a non-believers update at each step. So to wait all edges to become star, it's going to take just exponential time. So we're not going to do that. More remarks here that are important. So if the environment is actually coupled around the walker, it means there is a ball around the walkers where the edges are the same in both copies, then I could couple the walkers so that they do the same jumps. So if one jumps to the right, the other jumps to the right as well. This is good from one hand because it keeps the translation map phi equal, so it helps coupling the environment. On the other hand, it doesn't help coupling the walkers, just keep the distance between the walkers the same. So I have to do something different. So what do we do with the walkers? So we're going to do two different coupling strategies for the walker, depending on where the walkers are walking. So whether the environment around the walker looks favorable or not. And to describe this, what favorable means, we just tessellate space and time. So here space is horizontal, time is vertical. We tessellate the torus cross time in boxes. And we're going to say that a box is good if some events happen, and I'm describing 3 of them and omitting some, but this will be enough for our understanding. So I'm going to say a box is good if all the updates that occur to the edges in the box during the time of the box are oblivious. And recall that the probability of an oblivious update is close to 1, because P is small. The second thing I'm requiring is that each edge of the box receives an update, actually receives several updates, because this helps coupling the environments inside the good boxes. And finally, I want that the star edges, if I were to observe whether they are open or closed, they do behave like subcritical percolation. In particular, I require that the open clusters of star edges, if I ever observe them, are going to be at most of order, say, log square of the size of the box. Okay, so I need that the good box actually do not let the walker walks too much. Okay. So then, once we define this, we're adjusting the following things. If the random walk enters a good box or is passing through a good box, what happens is because there are several updates on the edges of the box and because they are all oblivious, I can couple the environment around the walkers as they are crossing this box. And second, if I start to get a scenario where the walker is inside the box and a lot of star edges are around, so I can actually do a simple random walk moment like we're doing dynamical percolation. So with positive probability, the walkers just do a step of single random walk inside the box. So that's the crucial property from good box, that each time the walker enters a good box, there's a positive chance that it does a simple random walk step. And if the walker does a simple random walk step in one copy, I can couple it, the second copy, with just use a simple random walk coupling. And this is not a simple random walk step, it's even a lazy simple random walk step. So I can really do the coupling of a lazy simple random walks. Your favorite coupling of lazy simple random walks. The problem is that what happens if the walker enters a bad box, then anything can happen because I'm not controlling what's happening there. Right? In particular, the distance between the two walkers could increase and could damage the coupling you are doing in the good box. But there is some hope that if the environment turns out to be coupled around the bad box, so in the bad box and around, then even if the bad box does some non-star updates, it's not a problem. I can still couple the non-star updates if the environment is coupled. And again, if the environment is coupled, I can do what I call identity coupling. I can make one walk just do the same steps as the other walk. Okay, so this gives me to the strategy of how to put this together. So let me tell you exactly how the coupling goes now. So the first thing we do, we want to show that the mixing time is at the most constant n squared over mu. So we observe boxes, whether they are good or bad, up to times c n squared over mu. From time 0 to c of n squared over mu. We observe all the boxes. Are they good or bad? Now you condition them, and here I'm drawing like 3 bad boxes and all the others are good. Now you condition this and observe the walker. So as the walker walks here, you observe it's walking in space-time, and if the walker, as the walker traverses good boxes, you always try to do this simple random walk coupling. You try to see if the walker is doing a step of simple random walk. If it's doing, you do a simple random walk coupling. If it's not, you just do identity coupling. And that's what we are doing here between the 2 copies. If the walker dares to approach a bad box like it's doing with this one, and what I mean by approach is around each bad box, I put some protective zone around it, that if the walker ever enters this bad zone around the bad boxes, I stop doing any simple random walk coupling. I just do identity coupling. And the idea here that if you do identity coupling here, from this point on, as the walker is walking in this region, the boxes are good, because this is what the protection zone is giving to you. And since it's good, traversing good box, you are only doing oblivious updates, so you can actually couple the environment in the whole region here. If the walker ever enters this bad box, then the environment is already coupled, and it can traverse this bad box with identity coupling succeeding. Okay? That's the strategy. The problem is that if I have many other bad boxes nearby here, maybe one here, one there, then things get funny, and just to a mode-scale randomization of this. But that's the main idea is in scale 1. I'm not going to really tell much about higher scales. The main idea is here. Okay, so that's exactly what I said. And one note that this is a non-Markovian coupling, in the sense that I need to observe the future of the environment to decide what coupling to apply to the walkers. Another thing I want to remark here, if I use this mode scale analysis, that the benefit you get from good box is not deterministic. Right? When you cross a good box, you cannot always do the simple random walk coupling, but that happens with a chance. So there is still a randomness in whether you can do simple random walk coupling or not in good boxes. So this requires a little bit of care on defining the events properly, so that you can still show that there is a positive chance of doing simple random walk coupling when you pass in good box, conditioning on the whole environment. Okay, that's my last slide. It is going to be giving you now an overall view of the whole proof. The proof overall has 3 phases, and what I described in the previous slide is phase 2. So it's just very simple. We observe here it's again space and time, so time goes up to c n squared over mu, and have a small phase that I didn't tell you before. It's just a small phase of length like log n over mu, and it's just you just let the 2 walkers walk. It could even be independently or try identity coupling. And the idea is that this is enough to couple the environments locally around the walker. Just a startup for you to have the environments coupled around the walker in a ball of radius 1. So you could just imagine that I just wait for the walker to be stuck, the 2 walkers to be stuck at a vertex with all edges around closed. This forced them to spend time 1 over mu stopped, and this is enough to just couple the environment around him. Just a simple startup so that the environments are coupled. Then we do the second phase, which is the bulk of the argument. It's what I described to you before. You observe good and bad box all the way to cn squared over mu. It is at all scales, and you observe the walker from the beginning of phase 2 until not the end, all the end, but until 2/3 of the end, or any constant fraction of the total time. So here I'm writing 2/3 of cn squared over mu. And this is where you, whenever you're passing through good box, you do the simple random coupling. If you enter these protective zones, you're just doing identity coupling, and you may never even not enter the bad box, but that's not a problem, you just did identity coupling. And you want to show that in this path that the random walker is going to do, you do a total of n square simple random walk coupling procedures. And identity coupling never fails when you applied it. That's what we show here. you stop it before, because otherwise you start entering the regions where you don't know enough information about the future because you're not observing anything above here. But when you get to here, you know that with positive probability, the walkers are in the same position and the environments may not be coupled. Because one important thing is that whenever you do a simple random walk coupling, you even uncouple the environments because you change the distance between the two walkers, you change the translation map. So when you get to this point, what you just do is you just let now the walker moves from this time to the end without observing anything else from the environment. Just let the walker moves, try to do identity coupling, hopes for the best. That's what you do. You can just show that it's just to get rid of future information. You need to get to a time where we have not observed the future yet. And you can just show that all these three phases occur successfully with positive probability. That's what this argument shows. And if any of them fail, we just start from scratch. Since they all work with positive probability, just need a constant number of repetitions and you're done, you're mixed. Okay? So that's the whole idea of the proof. So I'm stopping here and I'm happy to answer questions if you have. Thank you.
So you said at the beginning that the rate of the walk is much slower than the rate of the environment refreshing, right?
It's the opposite. The rate of the
opposite?
environment is lower than the rate is faster, but the environment refresh is lower than the walker moves.
So, and you said that mu and so this was the rate was going to 0 for the environment.
Yes.
So so I just must have missed it. What is mu here then?
That's mu n. I'm just dropping the n, but it's the same mu.
Okay, so does the rate which has happened not relevant therefore?
The rate is appearing exactly the mu.
Implicitly in the okay. And so if you slow the rate, if you don't have this, do you get anything interesting?
If mu is just a constant, right? It's just that, in other words, what I'm just doing is I'm making explicit the dependence of the mixing time on the rate mu. That's the only thing. It's just for, you could think mu could be anything here.
Right.
But yes, but you're not going to get any benefit if mu is growing to infinity. Right? If mu is going to infinity, the mixing time is not going to be faster than n squared.
So a basic question, I didn't get how you chose the good size of the protection zone. Because it's just automatic, it falls out from the time scale?
Yeah, there just need to be the computation, but just the time that needs for you to couple the whole environment inside that protective zone before you reach the bed box. And it has to be large enough because if by any chance the walker enters from the sides, it doesn't manage to get to the bed box.
Oh, because time is, So there's no like close expression for the good zone?
That is, just I don't know by heart.
There is a version of the thing, in the old Gen paper where, you do this kind of version where you are completely agnostic to the environment around you, and you can do the myopic version where you inspect, you only look at the environment around yourself and you pick uniformly from the available open edges. So does that create problems when you want to define your regeneration thing, or is it just a choice that you made?
Okay, the first is a choice just because it gets things reversible, and so it's just the basic is specialized. I know the stationary distribution. That's it. Now, does it make a difference for the regeneration? It does not. But yeah, I would have to think. But my guess is it does not make much of a difference.
Any other questions? Okay, that's just thank you, Alexandre, again.